Q&A space. Attendees can post their questions during the presentations, and they don't have to wait until the end. And then I will select questions to field to the two speakers in the Q&A portion of the webinar after the presentations. This webinar is also live streamed via the CBRA YouTube channel, and it is recorded and will be made available on the CBRA website, www.cbra.org, and the CBRA YouTube channel after the event. Finally, a disclaimer. Participation in a CBRA webinar does not constitute or imply an endorsement, recommendation, or favoring endorsement of the views, opinions, products, or services of the Central Bank Research Association or any other participating institution, individual, or entity. All views expressed during a CBRA or CBRA co-hosted event are strictly those of the authors, discussants, and other participants, and not those of CBRA, the co-sponsoring institutions, or any other participating institution. Okay, and then, so to get started, first is Brian Wheaton, Assistant Professor of Global Economics and Management from UCLA, who will be presenting Delayed Inflation in Supply Chains, Theory and Evidence. Brian?
Thank you very much, Hugh. Let me just share my screen here. All right, thank you everyone for coming today. I'll be talking about my joint work with Robbie Minton, Delayed Inflation in Supply Chains, Theory and Evidence. So the key questions that we try to answer in this paper are, firstly, how much and quickly do commodity price movements propagate through the network, affecting relative prices throughout the economy? And secondly, in the specific case of oil, how much and quickly do these relative price movements affect aggregate inflation? This is part of a broader research agenda that Robbie and I have on production networks, but these are the questions we'll be focusing on in this paper. So we're going to have both a model and some empirics in this paper. The model is going to be an input-output model with Calvo pricing. You can think of, for example, Lisa Rubo's job market paper. And for the empirics, we're going to make use of cross-industry shift-share design. So we're going to have both some reduced form OLS and IV regressions, but also more structural approaches, like minimum distance estimation, full GMM estimation. And we're going to obtain 5 key results, which I'll summarize for you in turn here. So firstly, network pass-through is more gradual than one might expect, at least more gradual than we expected. That is to say, for the average industry, pass-through of a persistent oil price change is 60% after 1 year and 80% after 2 years. So it takes some time to make it through. We find that this delay is a consequence of price rigidity interacting with the network. So basically, the production network is compounding rigidity. And holding the frequency of price adjustment constant, we show that more downstream firms pass through the shock more gradually, even when they're rationally forward-looking. Now, although that happens even when they're rationally forward-looking, deviations from rational expectations amplify this effect substantially. The network propagation of oil price movements we find is in line with rational expectations, but for other commodities, we find a much more gradual pass-through, so it's suggesting substantial inattention. Fourth, we find that relative price movements throughout the network due to oil largely pass through to aggregate inflation. And this pass-through explains the non-trivial predictability of core inflation from indirect effects of oil price movements. So that's the summary. In the interest of time, since I've only got 15 minutes here, I'll skip over the literature review here, but we do contribute to a few different literatures. And I'll get into the model. So in our paper, we have a general network, but again, in the interest of time today, I'll be presenting a simplified linear network just to fix the idea. So in the linear network, sector N uses labor and inputs from sector N-1. Sector 0 is the commodity, and sector capital N, the final sector, sells to consumers. So we have a sketch of this in the top right of this slide. In this case, the illustrating commodity we're using is oil. And each sector in this linear network has a cost share S in the intermediate input, what it's using as an intermediate, and 1 minus S in labor. We use standard New Keynesian firm pricing in each sector with constant returns to scale production. Each firm in the sector is able to change its prices at rate fee, so Calvo pricing. And firms may be rationally forward-looking, myopic, or anything in between. Now, as I mentioned, the paper has a general production network where can be high dimensional and phi may vary by sector, but this is just to fix the idea. Now, there are a couple of results we have in the theory section of our paper. So the first one that I want to illustrate here, first note that each sector has a network cost share of S to the power of N in oil. So for example, the petrochemical sector, as I said, it has a share S in refineries, and refineries have a share S in oil. So petrochemicals have a share S squared in oil. So the first proposition, this is the linear network equivalent of proposition 1 in our paper. Assume we shock the steady state with a one-time persistent unit increase in the commodity price at time t equals 0. Then to a first order approximation, long run pass-through is going to be the network cost share, S to the N, plus these general equilibrium wage effects. So it's going to relate very directly to the network exposure to oil. And remember, this is in the long run. This is as time t goes to limit infinity. You may also wonder, well, what about the transition dynamics? So to get to that long run, it turns out pass-through can be quite delayed, even for rationally forward-looking firms. So another proposition that we have in the paper is as follows. So consider an unexpected and fully persistent shock to the commodity price at time 0 again. If firms are myopic, that is, if they are not rationally forward-looking at all, then the duration of pass-through, the pace that it takes to get pass-through, is increasing in linearly in n. So as the number of, n, remember, is the number of notches down the supply chain that we are from the commodity. So it's increasing linearly, this in the case of myopia. But if firms are rationally forward-looking, then the duration of pass-through is increasing in the square root of n, the square root of the number of rungs down the supply chain. So you can see this illustrated in these two figures here. Again, this is for the case of the linear network. We have a fully general network in our paper. And it's clear that there's more delay in the case of myopia, but there's still some delay in passing things through in the case of irrational expectations. Okay, so we have a few other propositions in the theory section of the paper, but these are the two key ones that I wanted to go over today. So in terms of the empirics, I'm going to start with some reduced form empirics. And we're going to test in this first set of regressions whether the network exposure to a commodity, as opposed to merely direct exposure, determines the extent of long-run pass-through, and secondly, whether pass-through is gradual. So we're going to test things that are analogous to these two propositions I just showed you, essentially. And then we're going to specifically look at whether it's downstreamness, whether it is the number of rungs down the supply chain that you are from the commodity that slows pass-through, even conditional on frequency of price adjustment. So to do this, we're drawing on data from a number of different sources. So we're going to use the benchmark BEA input-output tables, BLS PPI, producer price index series, wage data from the QCEW, and frequencies of price adjustment by industry from Pasten, Schoenle, and Weber, and Diego Kanzig's series of OPEC-induced shocks to oil prices. We're going to focus on the 1997 onward NAICS period, but we have an appendix where we look at the SIC period as well, pre-1997, and find some results. Okay, so what we're going to test in these first sets of regressions, we're going to run basically the following specification. So we'll be regressing the change in industry prices on the network exposure of that industry to the commodity Z that we're interested in, times the change in the commodity price. So you can think of this as a test of that first proposition that I showed you. Is it the case that the extent of network exposure determines the extent of pass-through? And then we have a term, general equilibrium wage control term, to account for that second term in the first proposition I showed you earlier. And this network exposure, you should think of this as roughly the column of the total requirements input-output matrix, or the Leontief inverse associated with the commodity. And we're going to run this for a month-over-month difference and for a year-over-year difference. And I'll point out that if flexible pricing was true and we had full pass-through, we would get a beta equal to 1 in both cases. So this is a test of, is this pass-through that we're supposed to get in the long run actually occurring quickly in 1 month or 1 year? And so this first table is for a 1 month horizon, and what we see is coefficients below 1. So let me go through these briefly. So column 1 is using all oil price variation. We see a month-over-month pass-through coefficient of 0.5. That's well below 1, but it's non-trivial. We point out that if you take out refineries, which are a huge outlier in terms of both their share of exposure to oil and the rapidity of pass-through, because they're just one notch down the supply chain. They're right below crude oil. They have much quicker pass-through. So if you take those out, just a few observations, you get much lower pass-through. So that's what we do in column 2. You see the pass-through coefficient is about 0.25, 1/4 over the course of that first month. In columns 3 and 4, we repeat this exercise with the Kanzig variation, find a similar result. And column 5, we use non-oil commodities, again, a similar result, much less than the full pass-through. On this next table, we're doing the same exercise, but year over year. So again, we're finding coefficients of less than 1, but much closer to 1. Still, columns 2, 4, and 5, those coefficients are statistically different from 1 in each of those cases. So some pass-through has built up, and this suggests that things are filtering through over time, but we're still not quite there. So now more directly, we want to get at whether indeed it really is how far down the supply chain you are, the degree of downstreamness, as it's called, that's mediating this. So in columns 4, 5, and 6, we show that even after controlling for the frequency of price adjustment, which may plausibly be correlated with downstreamness, we still get significant effects, interaction effects of downstream. So this is saying that the further downstream a sector, the less rapid, and this table is over a month horizon, the less rapid the pass-through. So we get less pass-through over a 1 month horizon if a sector is far downstream versus if it's upstream. And I just want to briefly flag that, there are many other things one can think of as mediating the extent or pace of pass-through. So things like the concentration of the sector, the size of the firms, inventories, the capital share, et cetera. And all I'm doing with this table is pointing out that even if you throw in all of these things to the regression, the coefficient on downstreamness stays significant to the same extent. So there may be these other things going on as well, but downstreamness is still an important part of the story. It's not knocked out by these other effects. And I'll skip the robustness in the interest of time. We test robustness to a whole array of things. So now I want to briefly get into the structural estimation. So our GMM procedure is as follows. Given a calibration of firms' discount rates, MF, you can think of this as the myopia coefficient. The Calvo network model allows us to determine how long it takes an industry to pass through a shock. So in those previous regressions, we were in a sense, a little bit misspecified, right? We were using the extent of long-run pass-through. That's not using the full power of the model in some sense, because it can tell us month by month how much pass-through is supposed to be happening, supposing we know the discount rate. So we can run the regression given by the second equation on this slide, where we leverage that, where we take advantage of what it's telling us is going to happen month by month. And if we do this, then we should have beta equals 1, beta h equals 1 for all of the time horizons h, if the model is correct. Now, in order to do this, though, we need to know what the discount rates, the myopia coefficient, MF, is. So we're going to choose that to minimize the distance between the IRFs in the model and the data. And that's what our GMM approach is going to be. And so when we do that, the GMM optimal model finds statistically significant evidence of rational expectations in the context of oil, and pass-through that's very highly in line with the model. So if you look at the plot here, you can see that pretty much for almost all of the months, what's in the data and what's in the model are on the nose. So very close. And, you know, one other thing I'd like to point out briefly, in an appendix, we leverage oil futures data as sort of another approach to seeing whether there's rational expectations or myopia in oil and other sectors. So we can show in both reduced form and structural approaches that firms seem to be making use of oil futures. So if the futures market expects an oil price shock to revert almost immediately, then you get very little pass-through. A little bit of it upstream and very little of it gets passed through downstream because it's expected to revert pretty quickly. But a persistent a shock that the oil futures market expects to be persistent, that's passed through accordingly. So the firms are differentiating between these two in the context of oil. Skip these in the interest of time, but outside of oil, when we repeat this procedure for a variety of other commodities, we find complete myopia in the case of all other commodities for which we're able to do this estimation procedure. And, you know, we suggest that this may have something to do with oil being a lot more salient than these other commodities. So if you look at things like the number of news articles written about oil versus these other commodities, the amount of search volume index, it really is a big difference in terms of how much ink is spilled about oil, if you will, relative to all of these others. And, you know, on a day-to-day basis, when you're driving around, you see gas prices fluctuating at gas station posted prices. It really is something that's a lot more salient in your day-to-day life than a lot of these other commodity price fluctuations. So that's just our posited potential reason for why we find oil being a bit of an outlier in terms of how much attention people seem to be paying to it. Okay, so very briefly in the last couple of minutes I want to talk about an application. So we've characterized now how commodity price movements dynamically lead to relative price effects throughout the economy. And we're now going to focus on the effects of oil price changes alone for this application. So if we take the PCE, the personal consumption expenditure weighted average of these effects on relative prices, we can put these effects in the units of aggregate PCE inflation. And we're now going to regress core PCE inflation on the model's predictions for how current and historical oil price changes pass through to aggregate inflation. And so what you can see here is that across all columns, whether we use the all oil price variation or the Kanzig variation, indirect oil inflation has a positive and very statistically significant impact on core PCE inflation. So direct oil inflation, which refers to consumer gas purchases, that seems to have been successfully factored out by core PCE inflation as it should be. In fact, if anything, there's a slight negative coefficient in column 3, but once we use the plausibly more exogenous Kanzig variation, that goes away. But in all cases, there's a lot of an effect of indirect oil inflation on core PCE inflation. And you'll note that this is about, explains about 14 to 16% of the month-over-month variation in core PCE inflation, depending on whether you look at column 1 or 3. So it really is non-trivial. Okay, in conclusion, We show that long-run pass-through is given by an industry's network exposure to a shock, not just the industry's direct exposure. We show that pass-through is more gradual for downstream firms, and that firms pass through oil shocks in accord with irrational expectations, but act more myopically for shocks to other commodities. And the supply chain component of oil inflation is gradual and explains why core inflation is predicted by the indirect effects of oil prices. Now, thank you very much for your attention.
Okay, thank you for the presentation. If anyone has any questions for Brian Wheaton, feel free to submit them to the Q&A and we can address them at the end of the session. Next is Ricardo Reis, Professor of Economics at the London School of Economics, who will be presenting estimating the rise in expected inflation from higher energy prices.
Thank you. Oops, I just clicked the wrong thing, sorry. Very good. And everyone. Great, so thank you everyone for logging in. So can you just give me a thumbs up if you see my screen? Yep. Okay, great. Okay, so this is joint work with Paolo Patzelt, who's a great PhD student here in our department at LSE. And the question we're going to go after is really, well, it's pretty self-explanatory. It's in the title. What happens when energy prices, such like the oil prices that Brian was just talking about, goes up? What happens to expected inflation? You would think that we know that answer. You certainly would think so if you read the newspapers where people with great degree of confidence say that, of course, that when energy prices go up, expected inflation goes up. Indeed, if you plot real oil prices again in the US against expected inflation, this is the median of the Michigan survey, and to put them in the same scale here, I just subtracted the mean and divided by standard deviation, you say, boy, this is a pretty high correlation. Wow, it looks like people start expecting inflation whenever oil prices go up. That's what's going on with expectations. Sometimes it's used to dismiss expectations data. It says, look, this expectations data, it's all nonsense, it's all noise. Oil prices went up, people start saying expect high inflation. We know oil prices don't correlate all that well with core inflation. And so this is another nail in the grave of expectations. Others, in a policy sense, will say, well, if the central bank is supposed to see through oil prices, then they should see through expectations as well. And let's ignore the expectations data in some way. Or certainly, I've been in enough panels or read enough newspaper articles where this is mentioned. Now, as well-trained economists in this call will, I think, very quickly realize this is as bad as an econometric piece of evidence as you can present. Every single sin you've learned about econometrics is here. The integration order is all wrong. This is the level of oil prices against a change in prices, that is inflation. You haven't dealt with demand and supply. When people start expecting higher inflation, they start buying more oil. So there may be a correlation there in terms of spending that comes from one direction to the other. There's a huge omitted variable. Monetary policy responds to expected inflation, responds to oil prices. So this correlation could be entirely produced, attenuated, enhanced by monetary policy. And finally, correlation is not causation. All you did is plot two-time series. Why don't you plot shark attacks against temperature in the summer? You'll get a positive. That doesn't mean anything. So actually, we don't really know the answer to this question all that well. And we thought we can make a little bit of progress in it. Now, there has been a literature that does it. In the interest of time, I won't discuss it. I'll just tell you what we come in and do. The ECB has been running a consumer expectation survey since around 2020, which has the virtue that it has a lot more respondents than Michigan. Typical Michigan survey has 500 respondents. The ECB's has running at more than 20,000. Split around 11 countries, the shaded ones here, where you ask people about expected inflation 12 months ahead. Because you have so many people, you can not only exploit the cross-regional variation, but actually the expectations literature has shown that there's very systematic differences across groups in the population, men versus women, high income versus low income. So you can further split the data that way, and you have enough response that you can do it and end up with, by crossing against well-known sociodemographic characteristics and groups, end up with 88 different groups here of different characteristics that you have, with a few hundreds in each group, not just a few hundreds, 1,000 in each group, well, a few hundreds in each group, and in doing so compute relatively accurate expectations data with a cross-regional sense. Moreover, during this period, admittedly a short one, there was a ton of variation in electricity prices. And I want to emphasize electricity prices because electricity is much bigger in the basket than oil or oil products, and very visible, certainly during this time, to households who pay it all the time. Moreover, the market for electricity in these countries is very interesting in Europe because, one, there's a big variation in how much energy is consumed, say, in sunny south of Spain versus a little less sunny Finland. Moreover, there's a lot of variation in wind, which I'll tell you about why I used, as well as the oil price supply shocks, Kanzig type, affecting this market. Why do these affect this market? Because the way electricity is produced is, think about it as, we produce electricity in Europe using renewables, zero marginal cost, high fixed cost, horizontal supply curve. And then, given installed capacity, we then produce it using oil and gas, upward sloping marginal cost, upward sloping supply curve. What that means is that when you have a supply shock to oil, that is a shift in the upward sloping bit that affects the price of oil. But also, when there's variation in the amount of wind in northern Belgium versus southern Italy, what you have is that the horizontal bit of the supply curve shifts, and in doing so, itself generates changes in electric prices, which means that I have different sources of variation here in order to isolate exogenous shocks to electricity prices. So let me tell you how I use them. The way we use them, Paul and I, is to run essentially the following specification. We look at expected inflation of person I in country C belonging to socioeconomic group G at month T. And we build for each group and country and time a measure of anchoring expectations, which is basically an interquartile range of their long-run expected inflation, which again, I can measure because I have so many observations with some accuracy. I then am going to not regress expected inflation, but the 6-month change in this. Why? Because I know that there's large region group fixed effects, so I can difference those out. Germans always expect higher inflation than Italians. And on top of it, I can have country, group, and group fixed effects, as well as average past inflation to control for the fact that during these 3 years, there will have been systematic potential differences between Austrian inflation and French inflation. Having control for the country and group systematic differences, I can essentially, in running a regression like this with those controls on these two variables, de facto exploit the cross-regional variation in how anchored expectations were and what happened to electricity prices in that country and date to estimate these two coefficients, beta and gamma, that answer the following two questions. One, how much does expected inflation increase on average when energy prices rise by 1%? Two, how much more does the energy price raise expected inflation if expectations are more unanchored? And as it turns out, by the way, the unanchored expectation was approximately 1 percentage point increase in the interquartile range between 2021 and 22. So I can run this regression, and much like a lot of work in macro in the last 15 years has made progress by using cross-sectional variation in a monetary union to learn about the impacts of fiscal policy, I can learn about the impacts of oil prices on expected inflation, an old question, together with a new question. How does that vary with the extent of anchoring or unanchoring in the population? What is the answer? Briefly, when oil prices go up by 1%, expected inflation increases by roughly 1.2 basis points. If, though, expectations are unanchored, as much as they unanchored between 2021 and 2023, you get an extra 0.67 basis points on top. You can do this using more or less variation. Well, I won't tell you in the interest of time the other columns, but basically this is using individual. What if you add it up across groups? What if you use different measures of an anchoring? What if you include country group fixed effects? What if you include time fixed effects? And these are basically ways to slice what variation the data is driving it. The results move around as you'd expect as you have different variation, but across this and a lot of other ones, you do end up with results that are roughly consistent with this story that with this account that I just told you. But then you go a step further. This is the impact of 1% electricity prices, but you worry, 1% electricity prices, I would like to not worry, but you'd like to know, what if it's a supply shock? And here I can suggest to you to use 4 exogenous supply shocks, or 4 versions of them. Or no, 4? No, there were 3 of them. Anyway, column 1 is just a version of this column 1, but now in standardized units. But what we do in the other 2 columns is the following. Build energy shocks in the following, 4 ways. First, shift share. Let's use the electricity price change in the whole euro area, but at the fixed share of energy consumption weights, energy consumption in 2019. That is, I use the variation between Belgium and Portugal, and the fact that the change in electricity price we saw in the euro area exposed the Belgians way more than the Portuguese because they consume a lot more electricity. As usual in the shift shares, it's the exogenous shares 2019 and before that are driving the estimate. That's column 2. Column 3 says, hold on, I can not only have the exogenous shares, why don't I combine the exogenous shares with, on top of it, the exogenous shifts? How? By using Kanzig oil supply shocks. That is, use an exogenous change in the in the energy prices in the time series, together with the exogenous shares in 2019 of the amount of electricity. Finally, I can use, as I told you, these wind shocks. I look at variation in wind per country, per country and time, noticing that, by the way, the F-stat of that, if you were to run IV type regressions, I'm not running IV regressions, I'm running linear projections, local projections here, but the F-stats are like 50 and 60. That is, when there's a lot of wind in Belgium, the price of electricity in Belgium falls relative to Portugal in August, as opposed to, say, December and others. And when I look at those, what I find is, again, a strong, robust impact of an energy price shock in raising expected inflation, this affecting it through a higher impact if there's anchoring. Although, when I look at the wind result is no longer there. That's the 4th column. Also, the anchoring for the oil price shocks also kind of gets a little weaker. Well, to explain that, it turns out that if I go from a 6-month difference to a 12-month difference, all of a sudden the oil price shocks are completely consistent with the other ones, telling you there's something here about this choice of 6 months is not innocuous. So I do 6 months. If I do the shift share, the oil price, I get consistent results. But what about the wind? And to do that, let me plot for you the local projection. Again, I can use the electricity prices, the exogenous shifts, the exogenous shares, and exogenous shifts, or the wind. And those are the 4 columns here. And what you see, this is the endogenous one. And you see here the bias that comes from supply and demand mixing each other up. For all the other ones, you see the positive effect. But now you see that on the wind, for instance, relative to the oil, when you use the 6 months, you don't see much of an impact. But the reason is that the impact shows at 8, 9, 10, and 11 months. That is, you see that the impact accumulates later, which is actually consistent with all the other ones. So you end up with electricity prices affecting expected inflation, and they affect expected inflation with a delayed impact. And when that builds up over time, after 12 months, all of these decay, and by 18 months, they all go to 0. And that seems to be the dynamic effect of expected inflation. So, in the identified using cross-regional, Nakamura-Steinson being an important paper there, but generally just cross-regional identification pins down with quite a bit of accuracy and with even an attempt at getting some exogenous movements, what is the impact of energy prices, electricity prices on expected inflation. And that impact is actually sizable. These numbers are a little bigger than some in the literature before, and especially much more delayed in time. The literature often would find an effect that lasts for only 2 months. But let me answer some applied questions. How much then of the increase in expected inflation between the beginning of 2021 and end of 2022 was due to higher energy prices? Guys, it's 1%, 1.6 basis points. Energy prices roughly doubled during this time. Well, but doubling roughly will have increased expected inflation by more like 0.5 percentage points. In the data, expected inflation increased by 2.9 percentage points. On part of it, this is the fitted value of the regression. The partial R squared from the energy price is only 0.3. So actually only a third of this. In other words, it's true that energy prices affect expected inflation, but dismissing it through these arguments is wrong, is wrong quantitatively. The increase in energy prices explained very little of the high expected inflation, even if there's a strong positive statistical correlation between these two variables, and a much more convincing, I hope, than the one in slide 2. But second, the impact changes over time. Between 2021 and 2023, the impact of a doubling of the electricity prices, yes, that's what we're plotting here, more than increased. It increased from an impact of 40 basis points to as much as 1%, and then declined. Why? Because inflation expectations unanchored and re-anchored during this period. Let me ask a provocative question. Why is it that 6 months ago, when we had the problems in the Middle East, and there was a bump up in oil prices, expected inflation didn't change? Because by then, expected inflation had anchored. If we had had an oil shock or a problem in the Suez Channel 12 months or 18 months earlier, the impact of inflation would have been very high. Given when it happened, after the successful anchoring expectations, the impact was very small. A big hooray for the Fed for having been able to anchor expectations through its policies over the last 12 months. Third, you can ask, how does this link to theory? First of all, note that if I estimate the exact same equation, but instead of expected inflation, why not use actual inflation? The coefficients are about 6 times higher. That is, the impact of expected inflation is significantly lower than the actual inflation. In other words, there's some element of inattention on expectations. Guys, expectations are not overly sensitive to energy prices. They're actually undersensitive. They're significantly related, but actually the coefficients are quantitatively small. And then as a result, what do you expect from as we write in the paper, a simple rational attention problem? The impact on expected inflation of an increase in energy prices is going to increase with the unanchoring in the population. It's going to increase with the unanchoring. Why? Because when expectations are very sensitive to shocks, mistakes in form expectations must not be very costly. Agents must be paying little attention, and that's why you have a lot more unanchoring. But moreover, what that means is that this link between an anchoring and the impact of energy prices on expectations says that an anchoring itself, inflation expectations, create attention wedges that show up as markup shocks in the Phillips curve. In other words, and this is very consistent with what Brian was just doing, but a different argument on it, is that not only do oil prices generate the relative prices through Brian's argument of the impact it has on the relative prices across sectors because of price rigidities as well as the myopia, but on top of it, by generating heterogeneity in expectations, those same firms are going to set based on incorrect expectations. They're going to enhance even more the relative price distortions that Brian was talking about, and very consistent with what he found. Let me conclude. This paper did 4 things, or contribute to this lecture on oil price and expected inflation, a classic question in expectations, in 4 ways. It used cross-regional variation within a currency union. It used the data we used was released exactly, I think, 6 weeks ago only. We were just ready and jumped on it. Recently released very large household survey, which allows us to do this grouping and get enough cross-sectional variation. In the Michigan survey, you have 4 regions, 600 guys. You end up with cross-regional variation over 4 groups. You're not going to get anything. We show in the paper, everything's very precise. Third, we use the fact that our particular sample period is short, but has a huge amount of variability in this cross-region in time and energy prices. And fourth, we use the future of electricity markers to come up with not 1, not 2, but 3 exogenous new oil energy shocks for this literature. And in doing so, we conclude that price of electricity increased by 1%, expected inflation increases by by roughly 1.3 basis points. If an anchoring, the effect is much higher, that the impact actually rises, is not so short-lived. It rises for 8 to 12 months, but that the energy shocks explain a very small share of the rise in expected inflation we saw, and that the re-anchoring in 2023 really was very useful in preventing a flare-up just 6 months ago, and finally that some relative price supply shocks, and this again, very consistent with previous paper, may be driven by an anchoring itself. Thank you. I think I'm on time. Yes.
Okay. Great. Thank you for your presentation. We have some questions already. First, for Brian Wheaton, is there any evidence of asymmetry in the pass-through of oil price shocks to firm pricing?
Yeah, so thanks for this question. And it actually relates to another question about nonlinearities. So I'm going to answer those two at once. Let me share my screen and show a figure I think that will help get to this. So we've done a number of tests for these things, but this is probably the most succinct way of depicting this. So this is just a bin scatter of, on the x-axis, the total network cost change, and on the y-axis, the price change of an industry. So, one might wonder whether there are either, asymmetries between positive and negative changes, or whether there's like a substantial changes in slope as one zooms in or zooms out. So I also have another one of these figures where I, truncate it by chopping off some outliers and just focusing on small price changes. There really don't seem to be substantial or really noticeable at all asymmetries around positive versus negative. We were curious about this, so we took seriously this consideration and looked into it. But both by just looking at the data and some more sophisticated tests we ran, we weren't finding substantial evidence of either those asymmetries or of differences, substantial differences in slope, either when we zoomed in or zoomed out.
Okay, thank you. The next question is for Ricardo Reis. For policymakers, it is interesting to understand if some people unanchor differently than others. Can you learn more from your setup with its rich data variation?
Absolutely, yes. Again, the virtue of it is that you get these measures of the ACT that are very different across groups and very different across time. What can you learn? I don't know. I haven't looked at it, but that's a great suggestion to look at it. But in other words, you're right, because that's literally the variation I'm using to estimate the gamma coefficient. But you're right, literally plotting at it as opposed to just instead of using this variation to estimate it would be interesting in itself, and we should look at it. But yeah, that's the variation we use.
Okay. Next for Brian Wheaton, how should we think empirically about nonlinearities in price adjustment, especially since oil and other commodity prices tend to be very volatile? Is Calvo pricing a good approximation?
Yeah, so this is this also relates to that figure I was showing. We didn't really find substantial evidence of nonlinearities, as we thought perhaps it would be the case, and I think this may be what the question is getting at. Maybe there's some region around zero where there wouldn't be that much pass through one way or the other. And as I sort of was showing with that figure, even for those small changes, we do see a response in prices. So it doesn't seem to be the case that there's some small region where there isn't pass through of prices, then you have to go further out to get it. It does seem pretty consistent.
Okay, thank you. Ricardo Reis, I have a question. The result on past inflation is quite interesting. Can we perhaps interpret this as a memory effect? What happens if you take into account, say, past energy prices or lags of inflation experiences?
Yes, that's correct. I mean, you need to, that control is important so we generally know that past inflation has a strong impact on expected inflation. I mean, that's the sense in which adaptive expectations often works. It could also be memory effect. Like you said, I mean, if you put lagged expected inflation, it doesn't make a huge difference because it's very correlated with that past inflation in some ways during this period. We could do both. I don't think that would make a difference. It's just a good question. I don't think our regression allows us to learn more about that beyond, everything in our results confirm that this past inflation is capturing some memory, some learning effects. Yeah. And they're definitely there. It's very significant in all the regressions. It always shows up. Whether you do it the lag actual versus lag expected, not a huge difference, I think. But it's just you want to allow us to learn more. Looking forward in terms of using regional variation, of course. I mean, we are building on, as usual, on the shoulders of giants in some ways, insofar as our groups and anchoring relies very much on precisely was the difference across ages of people that the memory literature built itself on in terms of trying to look at means. well, I'm using those differences in age and in income and in region of life and others to build my groups and see the different and anchoring and so on. So in some ways, our anchoring measure is definitely building on that line of work, and it's captured in it, all its results.
Okay. I think we have time for maybe 2 more questions. Brian, there's a question. Do you have a theory for the role of the persistence in the shock on the duration and extent of pass-through? I'd also like to kind of tag onto that. I'm kind of curious if some of the firms might maybe think that shocks aren't persistent as they actually are, and that could be driving some of their responses. Brian, you're muted. We can't hear you.
Yeah, so this is a good question. It's part of the reason why we also did some analysis, which we have in an appendix on futures data. So there does appear to be evidence that oil firms are paying attention to whether the shock is expected to be persistent or expected not to be persistent by oil futures markets. So the cases where it's expected to be persistent behave like the persistent shocks that I sort of showed today. The cases where it's not expected to be persistent, where the shock is expected to revert almost immediately, essentially what happens is you get this like small amount of pass-through, never quite gets to a coefficient of 1 for the upstream firms that are like right below drilling of crude oil. But then for the firms that are way downstream, you get basically no pass-through at all, because by the time it would have made it out to them, the shock has totally reverted. So it does seem to be the case that that firms are paying attention to how these either paying attention to these markets or thinking about their own expectations, which may be correct around oil. We don't find that evidence when we repeat that exercise for other commodities. So they appear to be behaving in a more myopic fashion for other commodities, like copper, lumber, etc. Basically everything of it.
Okay. I think that's actually all the time we have for questions today. Thank you to our 2 presenters for presenting their research, and thank you to all the attendees for watching the presentation. Yeah, I hope everyone has a pleasant rest of the day.
Thank you, everyone.